IB Physics SL. This is paper 1A from the Specimen paper of the 2023 syllabus. Let's get started with question 1. A car has an initial speed of 16 meters per second. So 16 here is our u. It decelerates at 4 meters per second squared until it stops. So here, this is our a, but since it is decelerating, I'm going to write a negative sign in front of this. Then it stops, so that tells me that v is going to equal to 0. And then the question is asking for the distance traveled by the car. So we can use our kinematics, we can use our Suvat equations. The one we want to apply here is v squared is equal to u squared plus 2as. V, again, is is 0. U is 16, and then our A is -4. And then we have S, which is what we're trying to find. 0 squared is 0. 16 squared is 256. And then we have 2 times -4, so -8s. And if you didn't know 16 squared, you actually are allowed a calculator on this, so you can use your calculator. And then if we solve this, move 256 to the left, we get -256 is equal to -8s. Divide each side by -8. We have s is equal to 256 over 8, which you can use your calculator here again, is 32. So 32 meters is my answer. That is answer choice C. Alright, question 2 now. A block of mass 2 kilograms accelerates from a speed of 15 meters per second to a speed of 20 meters per second without changing its direction. What impulse acts on the block? Alright, so impulse is the change in momentum. And we can write the change in momentum as the momentum final minus the momentum initial. And since mass is going to be constant here, we can say mass times velocity final minus velocity initial is equal to impulse, because momentum is equal to mv. So now we can plug in our mass. We have 2 kilograms, and our final speed is 20 meters per second, and our initial speed is 15. So we have 2 times 5, and that is going to be 10. So the answer is C. Question 3. A net force of 8 newtons accelerates a 4 kilogram body from rest, so u is equal to 0, to a speed of 5 meters per second. What is the work done by the force? Okay, so work is equal to the change in kinetic energy. And again, like this previous question, we have kinetic energy final minus kinetic energy initial. So what is kinetic energy final? Well, kinetic energy is 1/2 mv squared. Our mass is 4 kilograms. And our final velocity is 5 meters per second. So we have 1/2 times 4 times 5 squared minus, again, 1/2 times 4, but this time we used our initial velocity, which was 0, so 0 squared. So if we simplify this, we have 2 times 5 squared which is 50. And then minus 0. So our answer is just 50 joules. That is answer choice A. Alright, question 4. A person stands in an elevator lift. Elevator. The total mass of the person and the elevator is 800 kilograms. The elevator accelerates upward at 2 meters per second. What is the tension in the cable? Okay, so here I think it's useful to draw a free body diagram or something that will help you visualize what is going on. Because if we have a weight of the person and the elevator that is acting downwards, and that is with mg. And we can find this. We know the mass is 800, and this is on Earth, so 800 times 10, so 8,000. That's the magnitude of the force vector. But then we also have a tension in the elevator cable. Let's call this T, because we don't know what value this is. What we do know is the net force. What is the resultant if we were to add these two together? So we can say that force net is equal to ma, which is equal to, well, the mass of 800 times the acceleration, which we're given as 2. So we have 1600 as our net force. And we can say that that is equal to T minus 8,000. Because this 1600 is our resultant force. So add 8,000 to each side, and we get T is equal to 9,600 newtons. And the answers are all in kilonewtons. So the answer that is correct is D. Moving on to question 5. An object is released from rest in a vacuum. So in a vacuum is telling me that there is no air resistance. But it's released from rest in a vacuum at a height h above the Earth's surface. As the object falls, it passes a point at a height of 0.75 h above the surface. And we're asked to find the kinetic energy of the object at a height of 0.75 h over the gravitational potential energy of the object at a height of h. Okay. So I think this might be a bit useful to think about in terms of total energy. So let's look at the gravitational potential energy of the object at height h. So this is at the maximum height where it's about, say it's about to be released. So since it's not moving, since its velocity is 0, then we have no kinetic energy. And the total energy is going to be the potential energy plus the kinetic energy. So 100% of the total energy is from this potential energy, from this gravitational potential energy. Now, after it has fallen by 0.25 h, 25% of that potential energy is going to be transferred into kinetic energy. And that is going to become the kinetic energy of the object at the height of 0.75 h. So we can say 25%. And you might be able to see this kind of sets up a fraction of 1/4. So my answer is B. Moving on to question 6. A bird of weight W sits on a thin rope at its midpoint. Alright, so it's evenly spaced on each side. And the rope is almost horizontal and has negligible mass. The tension in the rope is either less than W over 2, equal to W over 2, between W over 2 and W, or greater than W. Okay. So here we need to consider vertical equilibrium, because the weight down is going to be equal to the tension up if we consider this component here. So let's just call this magnitude of this tension some variable x. Well, therefore, right, x is equal to W. Because of vertical equilibrium, our net force is 0. Now, x is going to be 2 times t sine of theta. T is the tension here. Let me get rid of this t to make it less confusing. And I'm multiplying by 2 because we have the force, the tension, evenly distributed between 2 ropes on each side. So this t sine of theta is just from one side, and this is equal to W. Now, for small angles, sine of theta is equal to theta, in radians that is. So I can say that 2t theta is equal to W. W is weight. So let's consider 2 degrees, because this is a very, very small angle here. And let's consider it to be 2 degrees for sake of argument. Now 2 degrees is pi over 90 radians. So we have 2 pi over 90 times t is equal to W. This is just t over 45 pi. And that's equal to W. So obviously, t is greater than W. So our answer is D. Moving on to question 7. The internal energy of a real gas, so this is a real gas, is A equal to 0? Well, no. Let's think of an ideal gas. In an ideal gas, the internal energy is the total kinetic energy of the particles. But the reason it's an ideal gas is because we're assuming there to be no intermolecular potential energy. But in a real gas there is, so we need to factor in this energy into the internal energy. So the answer is D, equal to the sum of the intermolecular potential energy and the total kinetic energy of the particles. All right, question 8 here. The blackbody radiation curve of an object at 600 Kelvin is shown. The intensity units are arbitrary. What is the radiation curve of the same object at 450 Kelvin? All right, so this is a lower temperature. Now, with a lower temperature, we are going to have a lower curve. So this dotted line is the original curve. So it can't be higher. It can't be B, it can't be C. And then with a lower temperature, we are going to have a shift to the right. As the temperature increases, we get closer to the left, and it's decreasing, so we're getting closer to the right. And that is happening in A. In B, that does not happen, so it's not D. All right, the answer is A. Question 9. Star X has a luminosity L and an apparent brightness B. Star X is at a distance D from Earth. Star Y has the same apparent brightness as X, but is 4 times more luminous. What is the distance of star Y from Earth? Okay, so you can use the new data booklet for this, the 2023 Syllabus data booklet. And we can use an equation that is under B.1. We're given that the apparent brightness, let me consider for star x, the apparent brightness is equal to L over 4 pi d squared. And then for y, well, we have the same apparent brightness, so this is equal to 4L, because we're given it as 4 times more luminous, and luminosity is L, so 4L. And then over 4 pi d squared, but let me call this d sub y, because this is what we're trying to find. We're trying to find d sub y. Now, since these are equal, I can see that several things are going to cancel. First of all, the L's cancel, and then the 4 pi also cancels. We're left with 1 over d squared is equal to 1 over dy squared. So we can solve this further. Cross multiply, we get dy squared is equal to d squared. I'm missing this 4, there should be a 4 here. Yes. So instead of d squared, it is equal to 4d squared. So dy is equal to the square root of 4d squared, and that is just 2d. So the answer is B. Question 10. 4 identical resistors, each of resistance R1, are connected as shown. What is the effective resistance between P and Q? All right, so let me label these resistors. This is R1, this is R2, this is R3, and this bottom one is R4. Well, I can rearrange this circuit to get an equivalent circuit. Here, I didn't draw this that well, but here I'll have R1, so we have Q and P here now. And then this is in series all with R2, R3, and R4. I'm not the best artist, but those are connected. So all we have to do now is say that, well, R nat is equal to R times 3R over R plus 3R. Right? So this is just, well, equal to 3R over 4. So my answer is A. Here I set up an equivalent circuit which helped me understand what was going on. Alright, next, question 11. Conductor X is connected to a cell of EMF E. A power of 16 watts is dissipated in X. Conductor Y is made from the same material with the same diameter as X, but is twice as long. A cell of EMF 2E is connected to Y. Both cells have negligible internal resistance. What power is dissipated in Y? Alright, so we're looking at EMF. It says EMF here, but it also says negligible internal resistance. So I know the equation for EMF is we have EMF is equal to I times big R plus little r. And this little r is in the internal resistance, which is going to be 0. So we have EMF is equal to IR, and IR is equal to V, is equal to voltage. So we can use the equation from our data booklet that the power, I'll just apply this for X here, the power dissipated in X is equal to B squared over R. And this is equal to 16. We're given that. Now the power dissipated in Y is going to be P sub Y is equal to 2V squared, because we have 2E, so 2 here would equal to 2 everywhere, so 2V. And then that is over 2R, because we have twice as long, so we multiply by 2. And then that is equal to 4V squared over 2R. And we can simplify this. The 4 over 2 becomes 2. Then we have times V squared over R. And V squared over R is P of X. So this is equal to 2P of X. And P of X is 16. So we have 2 times 16, which is 32 watts. So the answer is C. Question 12 here. Two containers, X and Y, are filled with an ideal gas at the same pressure. The volume of X is 4 times the volume of Y. The temperature of X is 327 degrees Kelvin, and the temperature of Y is 27 degrees Celsius. Sorry, this is, I don't know why I said Kelvin. These are both in Celsius, so we do need to convert to Kelvin, and let's go ahead and do that. The conversion is plus 273, so this is going to be 600 Kelvin, or 200 plus 273.15 if you want to be exact, but that is not necessary in paper 1. And then here we have 300 Kelvin. And then this is an ideal gas at the same pressure. So what I'm thinking of right now is the ideal gas law. PV equals nRT. So let's apply this for the amount of substance in, or let's apply this for X, container X. P is equal to, well, the volume of X is 4 times the volume of Y. So V of X is equal to 4V of Y. So I'm just going to plug V of X in as 4V of Y right here. And that's equal to N sub X times R, that's a constant, times T. And T here is our 600 Kelvin. And then we're dividing by container Y. So again, we have P. This time it's just V sub Y. That's equal to N sub Y, R, and then 300 Kelvin. So the P's cancel. We're given that they're the same pressure. The V sub Y's cancel. The R's cancel. And 600 over 300 is 2. So we have 4 is equal to 2 N sub X over N sub Y. So divide each side by 2. We get 2 is equal to N sub X over N sub Y. And this is the ratio of the number of moles. It's going to be the same ratio for the number of substance. And assuming it's the same gas, also for the mass, because we can just multiply this by some constant C, and they cancel, so it's of course going to be the same ratio. The answer is C. Alright, question 13. An electromagnetic wave has a wavelength that is about the size of the diameter of an atom. Alright, so diameter of an atom is 0.1 to 0.5 nanometers. And we're asked to find what region, what region of the electromagnetic spectrum does this wave belong to? Alright, so you just have to know what ranges these are. I'll tell you that the answer is D, because X-rays we have 0.01 to 10, yeah, 0.01 to 10 nanometers. You'll have to fact check me on that, but I believe that is correct. The answer is D. All right, question 14. A particle undergoes simple harmonic motion of period t. At time t equals 0, the particle is at its equilibrium position. What is t when the particle is at its greatest distance from the equilibrium position? So greatest distance from the equilibrium position, that is amplitude. And let me draw a graph here. Here we're considering simple harmonic motion, so we'll be thinking of a sine wave. This is one period of the sine, and this is one period, which is t, yes, okay. Now, amplitude here is just 1/4 of t, and amplitude here is 3t over 4. Because this is half, so this is 2t over 4. I'm not sure why I wrote a pi, but this, yeah. And then lastly, we have 4t over 4, or just t. All right, and it's asking for the amplitude. So my answer would be 1/4t, but it doesn't have that. So I moved to 3t over 4. So yes, my answer is C. All right, question 15. Diagram 1 shows the variation with position of the displacement of a standing wave formed on a string. Diagram 2 shows the variation with position of the displacement of a traveling wave moving to the right along a string. Points P, Q, R, and S are points on the string. What is the phase difference between P and Q, and the phase difference between R and S? All right, so phase difference for the standing wave, diagram 1, should be fairly easy, because these waves are exactly in phase. They're creating a stationary wave, and P and Q are in the same segment. They're between the same two nodes, so they're going to be in phase. They have a phase difference of 0, so it's either C, it's either A. Okay, now look at diagram 2 here. Well, if we're counting these, we have 1, 2, 3, 4, 5, 6, 7, 8. And this R is located at 5. This S is located at 7. So this width here, or this path difference is 2. But this entire wave is lambda, so it is 2/8 lambda, or just lambda over 4. And the way we can find phase difference is by multiplying 2 pi over lambda times the path difference, which we found to be pi over 4. So the lambdas cancel. We are going to get pi over 2. So it's either C, it's either D. The answer then has to be C. All right, question 16. A mass of 0.25 kilograms hangs from a spring of spring constant 4 Newton meters. What Newtons per meter. What is the natural frequency of oscillation for this system? Okay, well, let's consider angular frequency, because we have the formula angular frequency is equal to the square root of k, the spring constant, over m, the mass. And applying this for our case here, we have 4 over 0.25 and the square root of that. Well, that's just 4 squared, and the square root of 4 is 4. So we have 4 radians per second. But now we need to convert to the natural frequency. And well, natural frequency is equal to angular frequency divided by 2 pi. So we have 4 over 2 pi. And that is roughly equal to 0.64. So the answer is B. All right, question 17. 2 long parallel wires P and Q are a distance d apart. They each carry a current. A magnetic force per unit length F acts on P due to Q. The distance between the wires is increased to 2d, and the current in Q is decreased to I over 2. Alright, so here's diagram. I'll label this diagram 1, and I'll label this one diagram 2. What is the magnetic force per unit length that acts on P due to Q after the changes? Alright, so we have an equation in our data booklet under D.3 where we have F over L is equal to the permeability of free space, that's mu sub 0, times I sub 1, times I sub 2, over 2 pi r. And we can manipulate this for our case here. So for diagram 1, well, we're given magnetic force per unit length, that's this right here. And we're given that as F, so we're just going to say F is equal to that constant times I squared. We have the same i's, so it's just I times I, which is I squared, over 2 pi, and the separation is d. Great. Now let's consider diagram 2. We have F prime is equal to mu sub 0 times I over 2. That's the difference. And then another difference is going to be our separation. We have a separation of 2d. So let's multiply this out. Oh gosh. Well, you should get this as your next step. And then this 2 is you can multiply 4 by 2 to get rid of this 2 here. So we're gonna have the permeability of free space times I squared times 8 pi times d. And take out 1/4. You have 1/4 times all of this stuff. So we have 1/4 of F, because this here is equal to F. So our answer is going to be B. All right, question 18. Planets X and Y orbit the same star. The average distance between the planet X and the star, I'll call this R sub X, is 5 times greater than the average distance between planet Y and the star. I'll call that R sub Y. So we can say that R sub X is equal to 5 R sub Y. This is an R here. Alright, now what is the orbital orbital period of planet X over the orbital period of planet Y. So T sub X over T sub Y. Well, I can apply Kepler's third law. T sub X squared over T sub Y squared is equal to R sub X cubed over R sub Y cubed. And R sub X is equal to 4 R sub Y. And that is being cubed. So I'm just going to skip a step here and say 125 R sub Y cubed. And then it's over R sub Y cubed. So these cancel. We're left with 125 here. But this side is being squared. So T sub X over T sub Y is going to equal the square root of 125, which is the square root of 5 cubed. That's the form the answer choice wants it. So the answer is D. All right, question 19. A charged rod is brought near an initially neutral metal sphere without touching it. So when the sphere is grounded, earthed, there is an electric current for a short time from the sphere to the ground. The ground connection is then removed. What are the charge on the rod and the charge induced on the sphere when the connection is removed? Okay. All right, so the metal sphere is going to be polarized. The charged rod, we'll consider this to be positive. All right, if I were to draw a quick diagram, our negative charges would be on the left side here. This is polarized. And we're going to have positive charges being discharged into the ground. This is the direction of conventional current. So these positive charges are leaving the metal sphere with a negative charge. So that is what is induced on the sphere. So it's either A, it's either C. Then the charge on the rod is just going to stay the same. It's going to be that positive charge. So C or D, making the answer B, C. C is the correct answer. All right, question 20. A positive point charge of magnitude 1 microcoulomb and a point charge Q are separated by a distance d. An electron is placed at a distance d from the 1 microcoulomb charge. The electric force on the electron is 0. What is Q? All right, so since the electric force on the electron is 0, this means that the forces are canceling out. I can say that the force of, let me label these. We'll call this 1, we'll call this 2, we'll call this 3, just to make it a bit easier. We can say that the force on the force by 3 on 1 is equal to the negative of the force of 2 on 1. Hopefully that makes sense, my notation here. So let's solve this. This I can write as K times Q times 1.6 times 10 to the negative 19. All right, this is charge 2, which is the electron. And you can find this value in this at the start of the data booklet. And then we actually have 2d, and that's squared. So that's the separation, that's the distance between them. Then this is equal to negative times k times 1.0 times 10 to the negative 6, which is the value we're given. And that's, again, times the 1.6 times 10 to the negative 19, the charge of the electron. And this time it's just being divided by t squared. So if we're trying to solve this, there are several things that will cancel out. Firstly, if I square this 2d, I get 4d squared, so the d squares cancel. And the 1.6 times 10 to the negative 19 also cancels, as do the k. So I'm left with q over 4 is equal to negative 1.0 times 10 to the negative 6. If I multiply each side by 4, I get q is equal to negative 4 microcoulombs. That is answer choice A. Alright, question 21. What is the sequence for the evolution of a main sequence star of about 2 solar masses? Okay. So it's not A, because I see red supergiant. This entire sequence here is telling me that we're going to need a much more massive mass, about 8 solar masses, I'd say. And that also means that D can't be right. We need much more mass. For C, well, a supernova isn't going to produce a white dwarf. It's going to produce a neutron star or even a black hole if there was a lot of mass. So it's not C. That means the answer is B. This makes sense. Question 22. The diagram shows the emission spectrum of an atom. Which of the following atomic energy level models can produce this spectrum? Alright. So, well, these are close together. These are close as well. Then we have a pretty big gap here. And then if I'm looking at A, well, these are close. We have a big gap. And then these are close together. And if I follow each emission line and match it up, my answer is going to be A. Alright, question 23. 2 radioactive samples X and Y have the same half-life. Initially, the ratio activity of X over activity of Y is 4. What is the ratio after 2 half-lives? Alright, so think of what a half-life means. That means the activity is going to decrease by 2 every half-life. Half the activity. So it's going to be over 2 to the power of 2 if we're having 2 half-lives. And we're doing that to each. So the ratio is going to remain unaffected because that will cancel out. So the ratio is still going to be 4. The answer is D. Alright, question 24. 3 statements about a nuclear fission reactor are: 1, that the heat exchanger transfers energy from the fuel rods to the moderator. This is incorrect. It transfers from the primary coolant to the secondary coolant, not the moderator. So 1 is not going to be part of our answer. We're asked what statements about the reactor are correct, and 1 is incorrect. Alright, moving on to 2 though. The control rods must be good absorbers of neutrons. So yes, this is a requirement because we need to be able to control the reaction rate and the fission that is occurring. So our answer needs to include 2. It can't be B. But it also can't be A. It can't be D because we eliminated 1 already. That means the answer is C. But let's look at 3. The moderator must slow neutrons down. So yes, this is correct. We need to increase the probability to induce further fission reactions. So C is the answer. And last question, there are only 25 questions in the 2023 syllabus for paper 1A. And we're given a diagram that shows two stars, X and Y. Now, note that the luminosity of X is equal to that of Y. So L of X is equal to L of Y. And through the Stefan-Boltzmann law, we also know that L is equal to 4 pi r squared times the Stefan-Boltzmann constant, and then times t to the power of 4. Well, since L of X is equal to L of Y, we can say that 4 pi r sub x squared times the constant times t sub x to the power of 4 is equal to 4 pi r sub y squared times the constant times t sub y to the power of 4. And here several things cancel. The 4 pi's cancel, the constant cancels, and that leaves us with r sub x squared times t sub x to the power of 4 is equal to r sub y squared times t sub y to the power of 4. And we can rearrange this to have r sub x squared over r sub y squared, and that is equal to t sub y to the power of 4 over t sub x to the power of 4. We can also further simplify this, take out the square here, and then take the square root of both sides. So we have r sub x over r sub y is equal to t sub y over t sub x squared. And t sub y over t sub x, well, we have the values for temperature. It's going to be 10,000 over 40,000. I'm going to just write that as 1/4. And that is squared. 1/4 squared is 1/16.